Hello everyone, today we're going to be discussing what a mutation is and how it relates to cancer, as well as taking a look at the mutation that is responsible for inherited melanoma. I'd like to first jump in on some background information. First of all, cancer is a mutation. It is when the cells in your body undergo uncontrolled cellular division due to the change in the cell's DNA sequence. This change is referred to as a mutation and happens when the DNA sequence is altered either by an incorrect base pair on the nucleotide, an insertion of base pairs where it's not supposed to originally be, or a deletion of pairs. As we can see in our picture here, there's something definitely a little wonky going on. Because DNA codes for the gene expression, which determines a protein's function, thus determining a cell's actions, a change in the DNA sequence can directly affect cellular function. Of course, mistakes happen, which is why we have DNA polymerase, which is an enzyme that helps synthesize and replicate DNA through means of making sure that the right base pairs are being added and copied to the DNA strand. These enzymes have the ability to go back on the strand and remove incorrect pair if detected. Adding to that, if a matured cell is detected, it is forced into what's known as apoptosis, which is when the cell is put to a controlled death. Unfortunately for us, sometimes these mistakes are not caught, which is why cancer exists today. Now, looking at our picture here, we have this normal cell undergoing some sort of DNA mutation, and notice how the color and the shape of the insides of the cell changed. That kind of represents the change of the function it's going through as its sequence is being altered, which is now showing it uncontrollably dividing, making it a cancer cell or cells. Specifically to cancer, these mistakes in the nucleotide or mutations create abnormal proteins that either increase the protein's activity or loses the protein's regulation. As an effect, cancer cells show an increase in invasiveness, a better survival in the bloodstream, a stronger resistance to the immune system, and a resistance to apoptosis. From there, the cells continue to divide and take the form of tumor, which is a growth of cells. These growths can either be benign or malignant. Benign meaning the cancer stays to a specific spot of the body, unable to spread, while malignant, which is more known and concerning form, invades neighboring tissues and can spread throughout the body. Now that we have an understanding of the physiology behind how mutations give rise to cancer cells, let's take a look at the inherited melanoma and how the gene cyclin-dependent kinase inhibitor 2A gene, or CDKN2A for short, can lead to this type of cancer when mutated. Before we get into that, what is inherited melanoma? Well, it's a skin cancer in which there is an uncontrolled growth of pigment cells known as melanocytes, which affects approximately 8% of people in the United States according to the American Society of Clinical Oncology. Along with this cancer is a genetic predisposition, where the condition arises in an autosomal dominant pattern, ultimately meaning your chances of developing melanoma increase if 2 or more first-degree relatives, such as a parent, have been diagnosed. Those expressing this type of cancer show dysplastic nevi, which are large irregular tumors typically located on sun-exposed skin. Here we see our cluster of proliferating melanocytes taking the form of our dysplastic nevi. Now knowing that cancer is a mutation, as discussed earlier, let's look into what kind of gene mutation that's required for melanoma to persist. The gene it affects, CDKN2A, is not just any gene. It's a tumor suppressor gene, which has the main function to keep cells from growing and dividing too rapidly, as well as preventing tumor formation. The gene codes for 2 major proteins, the P16LNK and P14ARF, which both help assist in regulating the cell cycle. And just to jog our memories, remember that the cell cycle is the process the cell takes in order to divide into another identical cell through what's known as mitosis. To do this, P16 binds to 2 other proteins, CDK4 and CDK6. These 2 proteins would usually stimulate the cell to continue through the cell cycle progression, allowing the cell to divide. However, when bound to P16, the 2 CDK proteins are blocked, thus unable to complete cell division. The other protein that our gene codes for, the P14ARF protein, protects another protein called P53 from destruction. P53 is another tumor suppressor that is vital for regulating apoptosis, and without it, the cell would lack signaling for self-destruction. Now, when the gene CDKN2A undergoes germline mutations, which is a mutation associated with sex cells, and this, of course, explains the genetic disposition behind developing familial melanoma. When the gene undergoes these mutations, two major things happen. For starters, because of the mutation, the P116LNK protein mutant would no longer be able to inhibit CDK4 and CDK6. Because of this, the cell transitions from the first gap in the cell cycle to the S phase, where the cell will proliferate uncontrollably. This outcome is the definition of cancer, and at the same time, the mutation of the gene results in the loss of function of the P14ARF protein that was essential for protecting the tumor suppressor protein P53 by binding to HDM2. And with the loss of this function, there's a direct loss to the P13 protein, hence no regulation of DNA damage signaling. As an effect, the cell can now avoid apoptosis, another characteristic of a cancer cell. Now, just to clarify, because I think this is a really great picture here, as we follow through on this left side of our chart right here, we're following through the function of the protein with no mutation whatsoever. We have P53 following through with apoptosis, whereas if this gene here was inhibited, if it was mutated, this also would be, and there wouldn't be any death signaling for the cell. Likewise, we have our P16LNK protein up here, and depending whether or not it binds to CDK4-6, depends whether or not the cell will continue dividing or it will be inhibited, as shown between these two options here. So, getting back to the big picture here, cancer is a mutation that alters DNA sequences, which ultimately changes the function of the proteins it codes for. Because of this, the mutated cells are able to become more aggressive, avoid cellular death, and divide uncontrollably, posing a problem to the host's body. There are plenty of steps you can take to avoiding the risk of attaining melanoma. However, coming from a family with prior exposure puts you as an individual at a higher risk. Some things to keep in mind would be always remember sunscreen, get plenty of antioxidants in your diet, and always and try to avoid carcinogens, which are cancer-causing chemicals. And I really want to stress the sunscreen. People don't take in consideration that UV light is a very big problem, especially with melanoma. I'd like to point out that a lot of the dysplastic nevi locations on people are where sun exposure is the greatest. So yeah, eat more berries, get those antioxidants, and try to avoid these carcinogens as demonstrated here. And thank you for watching. I hope this was educational. And here's some really good works cited that I got most of my data from, and of course visuals.